everyone. Yeah, thanks Taylor and Mary for leading the charge on this. I'm super excited to be with you here today. We're gonna be talking today about a little bit of a niche thing, also pretty new perspective on provider development. I would venture to say even experimental at this point, as only one provider has actually made use of this technique. But it's a very interesting technique nevertheless, and it managed to unblock us from a very long-running user request, which is Kubernetes custom resource definitions. And so with that, let's dive in. So Terraform providers, right? By this time into the talk, you've likely heard a bunch of my brilliant colleagues talk about different mechanisms to employ in building your providers. You've seen some different perspectives on building providers for Terraform. What I'm here to talk to you today is a slightly lower level mechanism. But before we dive into that, let's set the stage for everyone so that everyone has kind of like a baseline understanding of what a Terraform provider is and how it functions, so that we can move into more things, into more interesting things otherwise. Slight peek under the hood of a Terraform provider. They are essentially a gRPC server. Terraform CLI is the client for that. It basically starts up the provider as a standalone process after it has parsed the resource configuration that you as a user provide to Terraform. It'll have determined which providers are required. It'll have started them up, set them up as a gRPC server, and then it communicates with each and every provider instance via a gRPC link. And so that'll become interesting a bit later on. But what's important to remember is that the protocol, the underlying protocol that flows over this gRPC connection is actually modeled on the user interaction pattern. So the plan and apply sequencing, we will recognize that in the protocol elements that we'll have a little later on. And so on top of that, you normally have the provider SDK abstractions, which are the first thing that handle the protocol requests that the Terraform core makes into the provider. That traditionally the provider SDK is modeled from a CRUD perspective. So create, read, update, and delete on a per resource level. The resource operations and schema, as they are defined by the provider SDK, have long-term stability guarantees. And so the provider SDK is this component that we've had almost since the beginning of Terraform. Initially, it was bundled together with Terraform, and then was extracted as a standalone package, but still the same abstractions are kind of in place ever since the inception of Terraform. And so that makes it really easy to maintain compatibility with basically providers from the beginning onwards. As I mentioned, providers are standalone OS processes. They are, however, not launched by the user. They're launched by the Terraform core. But there is an opportunity to launch them as a normal terminal process when you're doing provider development. We won't be covering that, but I just wanted to mention it because it's an interesting debugging option that not a lot of people are aware of. Look for the --debug command line parameter to the providers. They have to have been specifically configured for this to work. Okay, so let's move on and have a look at the protocol that I keep talking about. So how does this actually look in real life? Let's take the example of a Terraform apply command. So when you go, you have some Terraform configuration, and then you go into the workspace, and then obviously you've had by this time initialized with Terraform init, and now you're about to apply the configuration. So you type Terraform apply and press enter. What happens actually at that stage between the provider and Terraform core? And so here I'm detailing a subset of the gRPC calls that are being passed around from Terraform into the provider and the responses that come back. So the very first thing that happens is that Terraform asks the provider for a schema. So you notice here, the very first call is the get schema call. The provider responds with a specific response for that call that gets the provider schema response type. In the gRPC definition, this includes attributes that convey the schema information for all of the resources that the provider can manage, but also the provider configuration block, the tiny set of attributes where you usually specify things like credentials or other options to the provider depending on the specificity of it. And so once the schema has been passed over to core, Terraform now knows how to interact with that provider and which resources it supports and which configuration options it takes for setting it up. And so there's a couple more calls being made here, and actually to validate configuration that are not specifically interesting for our use case. So that's why you see the dots. But then eventually you get this configure call. And this is really important. This is the very first call to the provider where actual information from the user is being passed to the provider. The arguments to the configure call carry over the values of the attributes that you've specified in the provider block. And so at this point, when the provider has responded from configure, Terraform has a strong guarantee that the provider is aware of its potential credentials to the target API, and it is able to talk to the target API. And so some more things happen here, other calls that are not interesting from today's point of view, but then we get to these two calls, the plan resource change and the apply resource change calls. So these happen in sequence, and the arguments to the plan resource change include the configuration for the resource that you've provided in a TF file, after which the provider responds with what it proposes to be the plan and eventually the actual resource action to be performed. And so the response from the plan resource change is then carried over into Terraform core and looped right back into the apply resource change. So the plan resource change prepares the field for the upcoming operation, and then apply resource change takes the output of plan resource change and among other things, establishes the connection to the target API and makes the actual API call that performs the resource operation that the user intended for that resource. And so this is all very low level stuff. This is not the perspective that you get from the SDK, from the provider SDK. It sits lower than that, but it becomes really important soon when we start talking about alternative to the SDK. And so let's first, again, discuss a little bit for everyone, what is the provider SDK and what is the alternative to that, which is the Terraform plugin Go package. So the Terraform plugin SDK is likely what most provider developers are most familiar with. It's the de facto standard for provider development. It's usually where everyone goes to start building a provider. It's the foundation onto which I would say 99.99% of the providers are built. It's a high-level abstraction. As I mentioned, it models resources in terms of schema plus CRUD operations, but that's not really how Terraform deals with them. Going back to the protocol for a second, Terraform deals with them in terms of the user actions, so plan and apply, but the provider SDK then translates those into CRUD operations from a provider developer perspective. So this is important because The CRUD mechanism is much simpler to use for provider developers, but it also is a little bit less flexible than what we're going to be discussing next. On top of that, you have a historical set of attribute types, which, as I mentioned, as the SDK aims to maintain very long-term compatibility and support all providers since the beginning of Terraform, and potentially all, or like at least as much as possible, earlier Terraform versions with working with new providers. It is very, let's say, cautious to make breaking changes. And so the limited set of attributes that I'm talking about is actually the set of attributes that predates Terraform 0.12. By comparison, Terraform 0.12 introduced a new type system, and a very interesting one at that. So we'll be talking and focusing on that moving forward. But just know that the mature framework for building provider developments is still Terraform Provider SDK, whereas Terraform Plugin Go is actually a newer mechanism, a newer component that's being released by HashiCorp to enable advanced use cases. It's also the foundation for Terraform Plugin SDK. So it's actually, it sits underneath Terraform Plugin SDK, but is also usable per se. It's a lower level abstraction, and it deals in terms of state and resource configuration plus plan and apply functions. So it actually very closely follows the protocol workflows as opposed to the CRUD mechanism in the SDK. It exposes the full Terraform 0.12 plus. So basically the type system that was introduced in 0.12 and has been available ever since in Terraform, it makes full use of that. And as I mentioned, underpins the plugin SDK. Okay, so now we know that we have a choice between Terraform Plugin SDK and Terraform Plugin Go. So which one to choose and what for, right? And our focus today is about dynamic resource types. And so what that means is a resource that can actually adapt at runtime, adapt its structure. And there's a very interesting use case for that, which I'm going to be going into shortly. But from the point of view of resource schemas, there's some really interesting differences, if you want, between Plugin SDK and Plugin Go that we need to look at, so we know which one to pick for our use case. And so, schema-wise, resource schemas are essentially the structural definitions that Terraform expects for every resource that it manages. Providers need to supply this to Terraform, as I mentioned earlier during the get schema call. And so they are defined with the SDK mechanisms. They have a smaller set of attributes in comparison to what the protocol supports. And they do not support, as I mentioned, the types introduced in Terraform 0.12 and onwards. There is also an ongoing project to basically refresh the SDK as a foundation for providers. This is called Terraform Plugin Framework. It's still a work in progress, but this will become the de facto standard sometime in the future. But now we have to shift focus to Plugin Go to actually see if it provides anything other that's missing from the SDK that we can make use of for a use case. And in Terraform Plugin Go, we still have to deal with schemas. Terraform requires schemas from all providers. This is not something you can get around but in comparison to the SDK in Plugin Go, you have access to all of the types that Terraform Core is able to deal with. And most specifically and most interestingly for our use case, we have access to the dynamic pseudotype attributes. Dynamic pseudotype is essentially a placeholder. We'll be talking about it shortly and having a look at how to use it. But basically, let's first think, why do we need a dynamic schema? What is a static schema? and why not just use the SDK? And so static schema is essentially what we recognize as the de facto schema mechanism in Terraform. I'm calling it static because the provider has to have all the schema information right at the beginning before it has any chance to explore beyond the local system. So the provider doesn't have access at the time when it needs to report schema to Terraform, it doesn't have access to the target API or any remote systems for that matter, because it hasn't yet been configured. Going back to that protocol workflow, we remember that get schema comes before configure. So because it hasn't been yet configured, it doesn't know about the target system, and this makes schema effectively an offline mechanism. By comparison, today's topic, dynamic resource types, are not truly a schema mechanism. They are still subject to the schema requirements of Terraform, but they are an alternative way of defining resource structure, still abiding by the schema requirements, but finding an escape hatch around the static nature of Terraform's de facto schema. And so what we can do in this case is we can leverage the remote APIs, our target APIs. If they provide any structural information about the resources they support, we're able to make use of that. And also we can change the supported set of resources at runtime, which is really interesting. Okay, so why would you do that? I hear you asking. Our use case, and the one that I found the most interesting, is for implementing Kubernetes custom resource definitions in Terraform. So by nature, Kubernetes supports defining new resources in the API at runtime. So effectively, you're able to declare and then use or manipulate API objects that have never been implemented in Kubernetes per se. This is really a unique trait of Kubernetes that I'm not aware of in any other platform API that I've dealt with. So custom resources are essentially fully configurable in terms of structure, and they are user dependent 100%. There's nothing about them that comes pre-baked into the cluster. Therefore, we don't know anything about their schema or their structure before they've actually been installed on the cluster. But luckily, Kubernetes was smartly enough designed to actually publish all of the structural information once these resources have been deployed to the cluster. They are in their structure information, and in fact, the structure information of any resource that's available in the API is available from the API server as an open API spec. So this is really interesting, and we're going to make use of that going forward. Okay, so how do they actually match up to Terraform's requirements? So Terraform, because it tries to be a very dependable tool, it wants to ensure safety of all of the infrastructure operations that users rely on it for. It has devised some safety nets and some checks and balances that are in place in order to make sure that whatever the user intends is actually what is expressed and then performed. And so to that end, Terraform tracks state and makes sure the state is consistent throughout the life cycle of the resources. So it will check whenever it gets new state back from the provider, whether the changes to that state actually abide by a set of invariants, so that the resource structure doesn't change, so that illegal values are not returned, and so on and so on. But this is something that's, let's say, non-negotiable with Terraform. It makes sure that the state stays consistent. On top of that, it requires structural information ahead of time so that it knows exactly what checks to do on which resource attributes. And so all of that packed together are things that as a provider developer, you need to keep in the back of your head when you're dealing at this lower level. By contrast, if you're working with the normal provider SDK, a lot of this is actually taken care for you by the SDK itself. But in our case here, we're on our own a little bit, so we need to be aware of that. What do we do? Because Kubernetes CRDs fundamentally are unknown ahead of time, whereas Terraform requires schema for everything ahead of time. And so the escape hatch there is we take the schema in our hands, so to speak. So we return a placeholder for the resource, and in all actuality, we will populate that placeholder as soon as we get structural information about the resource itself. This is really a very, let's say, unexplored mechanism, or has been until recently. But it's also very powerful, and it made us able to support dynamic resources and custom resources in Kubernetes. With that power also comes great responsibility, in the sense that you're now taking responsibility for maintaining the structural consistency of the resource. What that means, we'll see in a bit. And so let's have a look at this placeholder mechanism that I was talking about. So as I mentioned, there's a type system now in Terraform, and one of the types that are exposed there is the dynamic pseudotype. This is essentially basically a like a schema wildcard, if you want to call it like that. It basically says this attribute of a resource can take any shape in the future, but only once. Once we've actually established its actual concrete type, we have to keep that consistent. But it's enough for us to be able to delay specifying structural information until we actually get access to it. And so it's essentially like a declare now, but define later kind of mechanism. And so we tell Terraform that we are expecting an unknown structure of this attribute, but we will have more information about it later. And by later, I mean we delay it from the get schema moment all the way to the plan moment. Okay, so I mentioned the word once. What is that about? As I talked earlier, the Terraform core tries really hard to keep things consistent. And one of those consistency checks is that the structure or set of attributes defined for a resource does not change. And that doesn't actually make an exception for the dynamic pseudotype attribute that I showed earlier. What it actually means is that once you've set something concrete in a dynamic pseudotype attribute, you're committed to that type. And so the way to look at it is that you have to figure out as early as possible which structure of the resource you need. You have to send that back to Terraform, and you have to keep with it for the life cycle of the resources of that specific resource, right? We'll see shortly what that actually means concretely when working with the provider protocol. But let's have a look how that actually translates into the Terraform user experience, and how would such a resource actually present itself to the user. So what I'm showing here is output from the plan operation of the new Kubernetes provider that we're working on that implements this mechanism. And what's immediately apparent here is that although we're talking about two distinct resource types, namely a Kubernetes service and a custom resource definition, what we're seeing from the point of view of Terraform is essentially the same resource being manipulated, namely the Kubernetes_manifest resource, right? It's the same resource type as far as Terraform schema is concerned. We are, however, talking about very different structures internally. Okay, so that's already really interesting. We're able to essentially shift shape of the resource. But once we do that, as I said, we need to stay committed. So the same type that we've set during the first plan needs to carry over all the way through the life cycle of the resource. The way we extract this type, however, is also interesting because during the planning operation, when we actually move from the dynamic resource into the actual concrete resource, we are able to make API calls to the Kubernetes API. And so what that means is that we extract the open API type information off of the API server in real time during the planning phase and translate that into Terraform structural information. Right, so this is all nice and interesting, but it's also way more complicated than dealing with the provider SDK. So why would you actually do this? Should you always do this? Should you opt for this option whenever you start a new provider? And the answer in most cases is no. The provider SDK is there for very good reasons. It's mature. It has a very polished user interface from a developer perspective. As I mentioned, there's like a resource model with CRUD operations. It's really easy to wrap your head around and get started with. Going low level is actually a rather underestimated commitment in terms of work volume. It requires you to, because you're missing a lot of the SDK amenities, it requires you to actually re-implement some of them in your low-level provider. But on the other hand, you harness all of the untapped potential in Terraform that is because of the SDK's historical evolution not available at this time in the SDK. Namely, you get a lot of flexibility at plan time, whereas with the SDK, you're really limited on what you can do during the planning phase. It's mostly up to the SDK to provide the plan results. And you can use a lot of, well, actually all of the Terraform types, among which you have the dynamic one that we've discussed, but also object, which is a new one introduced in Terraform 0.12. Right, so with that said, I encourage you to actually give it a try. It's really easy to get started. There's already some information available, and there's actually one ready to use provider. It's this Kubernetes provider Alpha. It will soon get merged into the main Kubernetes provider, but this repository will stay around. And this is actually a more focused perspective into what it takes to work with Terraform Plugin Go, which is the framework that we're looking at here today. There is a work in progress, as I mentioned, for Terraform Plugin Framework, which is the new generation of high-level SDK that's being worked on right now, but it's not yet ready for consumption for production use cases. The alpha in the Kubernetes provider mentioned here is also a warning. Don't use that for any production use cases. We're still just moving from the alpha into the beta phase with it. But before anything else, just go ahead and check this excellent getting started guide on the Terraform docs, which explains in a lot more detail the interactions between provider and Terraform as I try to today. All right, so with that, thank you. And I'm open for any questions.
Wonderful. Thank you so much, Alex. That was incredibly informative and far more detailed than I would have ever imagined about writing a provider and just really understanding what goes on behind the scenes. You know, everything behind a plan, apply, and sometimes a destroy. Hopefully not too many of those, though. Like Alex said, if you do have any questions, please feel free to throw those into YouTube chat or Twitch, wherever you are viewing. If you're viewing this at some point in time in the future, I'm sorry, I don't think we can answer those questions, but you can always reach out to us and we'd be happy to do so. So please feel free to throw any questions you have into the chat. One that I had, Alex, was what was your, so obviously, working at HashiCorp, I'm sure slightly biased, but what is your thought on people getting started writing providers? And are there any things that are good to take note of or good to focus on when you're just starting to get up and running and working and writing a provider yourself?
Yeah, that's an excellent question, Taylor. Thanks a lot. That's actually coming up quite often, more and more so as the Terraform ecosystem expands and new developers are actually tapping their toes into the Terraform underpinnings. And so, yeah, to get started, I would recommend you do mandatory reading on that guide I mentioned as the first resource in my previous slide. So that guide on the Terraform documentation website is actually walking you step by step through all of the concepts that you need to be aware of when working with providers. There are bits and bobs there where it may have been lagging a little bit behind with the latest Terraform development. It's just that Terraform is right now in a very dynamic place in its life cycle. We've just released 1.0. There were a couple of major changes before that with the 0.12 version and the ones in between. So some of the developer-focused features have maybe not yet made it into the documentation. One of those is actually that there is now a simpler mechanism to start providers locally when you're developing. So I mentioned the debug option where you can actually start the provider ahead of time and attach a debugger to it. That's actually documented, but it's not linked into the guide itself, as far as I know. So you have to be aware that that exists and look for it in the Terraform documentation. The second is developer overrides as a mechanism to inject Terraform binaries from the local system rather than having them retrieved from the registry. So just Google Terraform dev_overrides and you'll run into the documentation for that, which is one developer pointed out to me not available directly from the guide. So we have to fix that. But in the meantime, just be aware that this exists.
That's one of my favorite things with documentation is PRs are welcome. If you see something, please, or issues are open too. Feel free to raise those up. If you don't have the time to be able to fix it or want us to take a look, please make an issue. If you do want to fix it directly, we need help with that too. So please feel free to open up a PR on that front. Awesome. Thank you so much. I've seen one of my favorite providers that I like to call out, I think is kind of, I feel like everyone's heard of at this point in time. If you haven't, definitely worth checking out is the Domino's Pizza provider. Really interesting way and use case to take a look at things. A wonderful way to end your pipelines too, right? A slice of fresh hot pizza. There are within the guides and how to use the Terraform provider SDK, how to work with that. I know that we also have some other tutorials up there too that just came out around Spotify as well, using the Spotify provider. There's also a blog post talking with the author of that provider too. So again, let imagination be your best friend when it comes to thinking about providers and different ways that you can use it. Just because it doesn't work exactly the way that you're familiar with, whether it comes to AWS, Azure, GCP, whatever, you can always create your own. So thank you for that wonderful reminder, Alex. Mary, did you have any questions for Alex?
Yeah, so in our experience, testing and working with dynamic resources has always been kind of an adventure. So I'd love to hear any tips and tricks you have when it comes to testing or poking at dynamic resources when you're troubleshooting, because as we know, they behave very differently than other resources.
Yes, you're very right, Mary. They are definitely less charted territory, let's call it, than what the established providers actually offer. And so, as I mentioned, this mechanism was only available in Terraform starting with Terraform 0.12 and then became available for providers to be built on with the introduction of Terraform plugin Go, which is less than a year old, if I remember correctly. And so, yes, we're still sort of like ironing the nicks out of it. That being said, the Kubernetes alpha provider is actually being tested automatically with acceptance tests. We've built those on a lower level shim that sits underneath the usual testing abstractions that the SDK provides, but you can just as well use the existing helper resource that you normally would for testing a provider, let's say a traditional provider. So you can use the same testing infrastructure and the same testing APIs in the SDK, or you can use the lower level ones. And I have to mention a new testing framework is also in the works alongside the Terraform plugin framework SDK that I mentioned. They are not a native or intended use case of Terraform. I'm talking about dynamic resources. So Terraform wasn't fundamentally designed for this. As I mentioned in the beginning, this is an escape hatch whenever you need to accommodate something like at runtime defined resources for which there really is no other way to do that in Terraform at the moment. But we hope to eventually evolve Terraform to the point where this can actually become a, let's say, a baked-in feature, an officially supported feature of Terraform. This is, I would say, with a star at the end, a little bit of a workaround rather than a recommended mechanism. But should you find yourself in that situation where, for example, we haven't been able to support custom resource definitions for several years, this has been a breath of fresh air, and we've actually we were able to deliver that.
Thanks. My motivations for asking that question were a little bit selfish, as we've been sort of looking at how to address some of the behaviors and auto-scaling groups in the AWS provider. As they are dynamic, a lot of things are defined as runtime. And so we've been looking at the work that the Kubernetes team has been doing as one of the ways that we could approach that problem. So thank you for the answer, because it is also helpful to me.
You're welcome. Happy to consult.
Awesome. Well, thank you so much, Alex, for just gracing us with that knowledge today. I hope everyone can learn from that and think of a fun provider that might be the right one for them, or just different ways in which they can help out on providers that already exist. So thank you again for your time, and we look forward to talking with you more here in the future.
Thank you too. Have a great show.